This is section 4.6, optimization. And in this section, we are going to use first and second derivatives to find optimal solutions to problems. And in this one, we're going to look at maximizing area. So the problem states a homeowner has $320 to spend building a fence around a rectangular garden. 3 of the sides will be constructed with wire fence at a cost of $2 per linear foot, and the 4th side will be constructed with wood fence at a cost of $6 per linear foot. And it states that we are to find the dimensions and area of the largest garden possible that can be enclosed with $320 worth of fencing. So if we look at the image they gave us here, they're using the variable y for the width and the variable x for the length. So we can rewrite those variables on the other sides that weren't labeled. And we see that we have $2 times y, $2 times x, $2 times y, and $6 times x for the one wooden side. This lets us put together our cost equation. So 2y plus 2x plus 2y plus 6x. And we can combine the like terms. That will give us 4y plus 8x. And the cost that we're going to be restricted to is $320. So this is our equation that we developed from the perimeter with the cost. And this is actually our constraint equation. This is what's limiting the dimensions of our garden, the cost limit. So our goal is to maximize area. So we need to write a function for area. So we'll say area equals length times width, which is x times y. And if we can solve our cost equation for one variable, we can substitute it into the area equation. So this equation here, the 320 equal to 4y plus 8x, I can rewrite that as 4y equals 320 minus 8x, then divide both sides by 4, and we get y equals 80 minus 2x. We can take that 80 minus 2x and replace the y variable in the area equation, and this will give us x times 80 minus 2x. And now that there's only one variable, we can write this and say that it is the function a of x, area as a function of x. A of x equals, and I'm going to distribute this x through the parentheses. So that gives me 80x minus 2x squared. The first derivative, a prime of x, will be 80 minus 4x. And if we solve a prime of x equal to 0, we get x equals 20. Now we can find the second derivative, a double prime of x, which is negative 4. Notice there is no x variable left, so this means that it is concave down for the whole domain. And if the graph is concave down, that means that the critical point we just found represents a maximum. So a double prime of 20 is equal to negative 4. Because there's no x to plug into, that means it is a maximum, and we found the maximum area. The max area occurs when x is 20. We can plug that x is 20 into this equation for y right next to it here. 80 minus 2 times 20 gives us a y variable of 40, and we have found the dimensions. So the dimensions that we want here is 20 feet by 40 feet, and this creates a max area equal to 800 square feet. So here's the textbook outline on how to solve problems like this. They give us some steps. You can pause here, read over the textbook steps, and when you're done, unpause. We'll do a second problem which relates to the previous one. What we did with this first problem was to maximize area with a restriction on the cost for the perimeter. And now we will minimize perimeter in an effort to reach a targeted area of 1,250 square feet. So let's read through this problem. It says, refer to example 1, that is the problem we just finished. It states that the homeowner judges that the area of 800 square feet just is not big enough and decides that they want an area of 1,250 square feet. So they're going to push the area bigger, but as they're doing this, they would like to keep cost at a minimum. So they want to maximize area while minimizing the cost. That means we want to minimize the perimeter. So we have an area function equal to x times y, and now x times y is going to be equal to 1,250. We have a cost function equal to $2 times the length of y plus $2 times the length of x plus $2 times the length of y again plus $6 times the length of x. This cost function is 4y plus 8x. So because the area equation is set equal to a number, we're going to solve this equation for y. So it gives us y is equal to 1,250 over x, and we're going to plug that 1,250 over x into y of the cost function. And 4 times 1,250 is 5,000, so cost function now has one variable, we'll call it c of x, equals 5,000 over x. And I would like to combine these fractions, so I'm going to multiply 8x over 1 by x over x, so that I can write this as 8x squared over x. Now that we have like denominators, we can say that the cost function is 5,000 plus 8x squared all over x. And we would like to minimize this. So to do this, we will find the first derivative, c prime of x, and I'm going to use the quotient rule here. Quotient rule says take the bottom function, multiply it by the derivative of the top function, and then subtract the top function and multiply that by the derivative of the bottom function. Put all of this over the bottom function squared. And now I'm distributing this subtraction from the numerator, and I see that I can combine my x squared terms. So c prime of x simplifies and gives us 8x squared minus 5,000 all over x squared. And if we set this equal to 0, a fraction is equal to 0 only when the numerator is 0 and the denominator is non-zero. So we say what value for x would cause this numerator to be 0? So 8x squared minus 5,000 equals 0. I'm going to add 5,000 to both sides. This gives me 8x squared equals 5,000. And if you divide both sides by 8, you get 625. And the square root of 625 is 25. So if x is 25, we can go back to our equation here for y, and we can say, well, what is 1,250 divided by 25? And you would find that y is equal to 50 then. And these are our dimensions, but let's just double check. Does this actually minimize? Let's go to the second derivative test. So we're going to find c double prime of x, take the bottom function, multiply it by the derivative of the top function, subtract the top function, and multiply it by the derivative of the bottom function, and put all of this over the bottom function squared. And now we're just going to do some simplifying. And we see the 16x cubes cancel, and we're left with 10,000x over x to the fourth, which simplifies to 10,000 over x to the third. And if we put 25 into the denominator, since it is positive, 25 cubed will be positive, and a positive divided by a positive is positive, and that tells us the graph is concave up at x equals 25. And if it's concave up, that means that this critical point represents a min. So now we can take these dimensions that we found. X is 25. And y is 50. And we can use this to then determine what is the minimum cost. So we're going to multiply y by 4. So 50 times 4 is $200. We're going to multiply x by 8. 25 times 8 is $200. So 200 plus 200 gives us a minimum cost of $400. And that is to create a rectangular garden fence that has an area of 1,250 feet. So this next problem is moving away from area and perimeter, and now we're looking at revenue, cost, and profit. If we read through it, it says an office supply company sells X permanent markers. So X equals the number of markers that are being produced or sold. So an office supply company sells X permanent markers per year at P dollars per marker. The price demand equation for these markers is P equals 10 minus 0.001x. What price should the company charge for the markers to maximize revenue? So we have the price function, we have to create the revenue function. Remember that revenue is equal to the number of objects multiplied by the price of the object. So the revenue function is going to be x times 10 minus 0.001x, and we can say that the revenue function is 10x minus 0.001x squared, and we want to find a maximum revenue, so we're going to look at the critical numbers. We're going to say R prime is equal to 10 minus 0.002x, and when we set that equal to 0 and solve, we get x equals 5,000 markers. It says, what price should the company charge for the markers? Well, we needed that x to plug back into the price function. So little p for the price, I'm saying little p because big P would be profit, little p of 5,000 is equal to 10 minus 0.001 times 5,000. And that tells us the price is $5 per marker. Then it asks what is the maximum revenue. So we want to plug that 5,000 into our revenue function. So 10 times 5,000 minus 0.001 times 5,000. And we want to square that. And we get $25,000. So that is the max revenue for 1 year just from the sale of these markers. Next, we want to maximize profit. And the problem says the total annual cost of manufacturing X permanent markers for the office supply company is given by this cost function. And this is the annual cost for X markers. Next, it says, what is the company's maximum profit? Well, to calculate profit, we need to define the profit function. And profit is equal to revenue minus cost. So we need to say that profit is equal to, we'll write the revenue function, 10x minus 0.001x squared. And from that, we will subtract 5,000 plus 2x. The profit function can be written as negative 0.001x squared. I can combine the 10x with the minus of the 2x, so that leaves us with 8x, and then subtract the 5,000. And we have expressed our profit function as a polynomial in standard form. Now, I'm going to reread the problem. It says, what is the company's max profit? What should the company charge for each marker? So once we solve for x, we need to plug that x back into our profit function to find the max profit, but we also need to plug it back into the price function. Remember the little p function, to find what price we should be selling the markers at to obtain maximum profit. So again, we start with the first derivative so we can get our critical numbers. The derivative of profit is negative 0.002x plus 8. And we want to set that equal to 0 and solve for x. So we get 8 is equal to positive 0.002x. And we want to divide 8 by that decimal. 8 divided by 0.002 tells us x is 4,000. And now we can find the profit at 4,000. And this gives us a maximum profit of 11,000. The price, that's little p, we need to take 10 minus 0.001 times x, which is 4,000. That will give us a price of $6 per marker. So 11,000 is our max profit. $6 is the price for the markers. And 4,000 is the production level for us to reach maximum profit in a year. We modify this problem and say, what if the government imposes a $2 tax on each permanent marker from the previous example? Modify the cost function and determine how many markers should be manufactured to optimize profit. what is the profit, and what should the company charge for each marker to realize this maximum profit. So if we go back and we say, well, this was our cost function, but now we're going to add a $2 tax on each permanent marker, that means the cost function, C of x, is now 5,000 plus 2x, which is what we started with, plus an additional 2x. This is the tax. So the cost function is 5,000 plus 4x. So we have our revenue function, R of x, is equal to 10x minus 0.001x squared. The profit function is going to be 10x minus 0.001x squared, subtract the 5,000 plus 4x, and we're going to simplify the profit function and express it as a polynomial in standard form. We'll find the derivative so that we can locate the critical point. And now we find that we should be producing 3,000 markers per year. The maximum profit is profit at 3,000. And now we have a maximum profit of $4,000. And what should be the price, or what should the company charge for these markers? Now we want to evaluate little p at 3,000. And that would be 10 minus 0.001 times 3,000. And that would be $7 per marker. So this next problem is called inventory control. A multimedia company anticipates that there will be a demand for 20,000 copies of a certain DVD during the next year. It costs the company 50 cents to store a DVD for a year. Each time it must make additional DVDs, it costs $200 to set up the equipment. How many DVDs should the company make during each production run to minimize its storage and setup costs? So we've stated here that we're going to let the variable y be the number of production cycles and the variable x be the number of DVDs produced in each of those production cycles. From that, we can see that x times y, the number of cycles times the number of DVDs produced, will equal our 20,000 DVDs. On top of that, we have a cost equation that says it will cost them $200 to set up the equipment to make additional DVDs. So 200 times the number of production cycles, y, plus the 50 cents to store the DVDs for a year, and times the number of DVDs, x. So this is our system of equations. Here is our constraint equation. And we're going to solve this equation for y. So y is equal to 20,000 divided by x. And we can then take this expression and plug it into the y of our cost equation. Now we can see that cost is equal to 200 times 20,000 over x plus the 50 cents times x. And if we simplify this equation, we get 4 million over x. And we want to get a denominator of x here, so we'll multiply top and bottom by x. So we're going to add 0.5x squared over x. And now that we have a function of one variable, we can call it c of x equals 4 million plus 0.5x squared all over x. Now our goal for this cost equation is to minimize. So we're going to find our critical number, c prime of x, and we'll use the quotient rule. It says to take the bottom function, multiply it by the derivative of the top function. We see that 4 million is a constant, so the derivative is 0, and the derivative of 0.5x squared is 1x. We're going to subtract from that the top function, which is 4 million, plus 0.5x squared, times the derivative of the bottom function, which is 1. Put the whole thing over the bottom function squared, and this is our c prime of x. We're just going to simplify it a bit. We see that we have x squared minus 4 million minus 0.5x squared all over x squared. And we can simplify this one more. So we have x squared minus a 0.5x squared. We can combine those. And here we have our derivative of the cost function. And we want to set this equal to 0 to find the critical numbers. Now the fraction will only be 0 when the numerator is 0. So 0.5x squared minus 4 million equal to 0. We'll add 4 million to both sides. I'll change the 0.5 to a 1/2. And from here, we should see that x squared is equal to 8 million. And if we take the square root of 8 million, we get about 2,828. And if we take that x value and plug it back into our y equation that we came up with here, we see that y is about 7. Now, with this solution, it is the minimum solution based on the constraints that we've put in place. And this would get you 90% of the credit for this type of problem. But this problem has an implied component. And that is that the cost function can actually be reduced even further. And to understand that, let's look at the next slide. So what I've set up here is a chart saying that suppose we produced 100 DVDs and they're in storage. So the first day they're in storage and we see that we sell 20. And after one day, we've gone from 100 to 80 DVDs that we're paying for storage on. And then from the second to the third day, another 10 sell. From the third to the fourth day, another 5, and another 10 sell, and another 15, and another 10, and then 5, and then none sell, and then the last 10 sell. If we look at this, we can see that on day 0, we had 100 DVDs. On day 1, we were storing 80. On day 2, we were storing 70. And if we add these all up, we have 430 days worth of storing DVDs. And that was over the course of 9 days. So if we take the 430 and we divide by 9, 430 divided by 9 tells us that 47.7 repeated. So we'll say about 48 DVDs were being stored for that course of time. We started with 100 and we're at 48. And now, of course, you can create additional charts. Let's say that this represents one production cycle. Other production cycles might have graphs that look a little bit different, a little bit higher, different lower. And as these different production cycles happen, they might have averages of 51 out of 100, or 53 out of 100, or 45 out of 100. But what you'll notice is that if you take the average of the production cycles, you will get 50 out of 100. And that means that we're not paying for the storage of all of the DVDs for the entire year. We're going to only be paying for storage on half of the DVDs for the year. So since we are only paying for storage on half of them, we're going to modify our cost equation. So our cost equation is $200 per cycle Y plus 50 cents per batch X. But now we're not paying 50 cents on the entire batch, we're paying 50 cents on half the batch. So the cost equation becomes 200Y plus 50 cents times half X, and 50 cents times half X gives us a new cost equation of 200Y plus 0.25X. And now we will redo this problem using this cost equation. Recall, we had X times Y equals 20,000. So Y was equal to 20,000 over X. And we can take that and plug it into the Y. So now we have cost is equal to $4 million over X plus 0.25 X squared over X and now when we take the derivative C prime of X, it is the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. And let's simplify this further. We see that we have 0.5x squared, and we're going to subtract 0.25x squared. So we have 0.25x squared minus 4 million all over x squared. And we said that the derivative of cost will be 0 when the numerator is 0. So we have 1/4 x squared equal to 4 million. That means that x squared is equal to 16 million, and that x is 4,000 DVDs. And with 4,000 DVDs being produced on each production cycle, when we go back to our equation for Y and plug in 4,000 for X, we see that Y is equal to 5 production runs. And that is the solution for minimizing cost of producing and storing these DVDs for the inventory control problem. So this is the end of the lecture. Rewatch the video, take notes, and complete the practice problems online, and then come to class with questions.